Hello and welcome. In this video, we'll explore the mathematics behind one of the most fundamental machine learning algorithms, linear regression. The goal of linear regression is to find a straight line that best represents the relationship between a set of input data points, x, and their corresponding output values, y. This line is described by the familiar equation y equals mx plus c. Here, m is the slope of the line, which tells us how much y changes for a 1-unit change in x. C is the y-intercept, the value of y when x is 0. In machine learning, our goal is to find the specific values of m and c that create the best-fitting line for our data. What does best fit actually mean? We quantify it by measuring the error, or the difference between our line's prediction and the actual data. For each data point, x sub I, our line predicts a value which we'll call y hat sub I. It's calculated as m times x sub I plus c. The error for this single point, called the residual, is the actual value, y sub I, minus the predicted value, y hat sub I. To get a total error measure for all our data points, we can't just sum these residuals, because positive and negative errors would cancel each other out. Instead, we square each residual. This makes all errors positive and also penalizes larger errors more heavily. Then we sum up all these squared residuals. This gives us our cost function, often called the sum of squared errors, or SSE. We'll denote it by j. J is a function of m and c, and our goal is to find the values of m and c that make j as small as possible. This process is called ordinary least squares. To find the minimum value of our cost function j, we'll use a key tool from calculus, derivatives. The minimum of a function occurs where its slope is 0. Since j depends on two variables, m and c, we need to find where the partial derivatives with respect to both m and c are equal to 0. Let's begin by finding the optimal value for the intercept, c. We will take the partial derivative of j with respect to c and set it to 0. Here's our cost function again. To find the derivative, we apply the chain rule. The derivative of a squared function u squared is 2u times the derivative of u. We can bring the derivative operator inside the summation. The derivative of the inner part, y sub I minus mx sub I minus c, with respect to c, is simply -1. So the partial derivative of j with respect to c is the sum of 2 times the residual, multiplied by -1. Now we set this expression to 0 to find the point of minimum error. We can simplify this by dividing both sides by -2, which leaves us with the sum of the residuals being equal to 0. Next, we can distribute the summation operator across each term inside the parentheses. The sum of a constant c over n data points is simply n times c. And since m is a constant with respect to the summation, we can pull it out. Now we can rearrange the equation to solve for our intercept c. Dividing both sides by n, we get c equals the sum of y over n minus m times the sum of x over n. You might recognize these terms. The sum of y divided by n is the mean of y, which we write as y bar. Similarly, the sum of x over n is the mean of x, or x bar. And there we have it. The formula for the optimal intercept is c equals y bar minus m times x bar. This has a beautiful intuition. It means the best fit line must always pass through the average point of the data, x bar, y bar. Now that we have a formula for c, let's derive the formula for the slope m. We follow the same process. Take the partial derivative of the cost function j, this time with respect to m, and set it to 0. Again, we use the chain rule. The derivative of the outer square gives us 2 times the inner term. The derivative of the inner term, y sub I minus mx sub I minus c, with respect to m, is -x sub I. So the partial derivative is the sum of 2 times the residual, multiplied by -x sub I. We set this equal to 0 to find the minimum. Dividing both sides by -2 simplifies the equation. Now we have the sum of x sub I times the residual equals 0. Let's distribute the x sub I term. Next, we apply the summation to each term. Since m and c are constants with respect to the sum, we can pull them out. This leaves us with our second normal equation. We now substitute the expression for c, which is y bar minus m times x bar, into this equation. This step is crucial because it will allow us to isolate m and solve for it. Let's expand the last term by distributing the sum of x sub I. Now we need to isolate m. Let's move all terms containing m to one side of the equation and all other terms to the other side. We can now factor out m from the terms on the left side. Finally, to solve for m, we divide the right-hand side by the term in the parentheses on the left. While our expression for m is correct, it's typically rewritten by substituting the definitions of the means and multiplying by n over n. This gives us the final standard formula for calculating the slope. It's worth noting that this formula can also be written in terms of covariance and variance. This alternative form is often preferred for its statistical interpretation and numerical stability, but it is algebraically equivalent to what we just derived. Let's summarize what we've accomplished. By defining a cost function based on the sum of squared errors and minimizing it using calculus, we have successfully derived the closed-form solutions for the parameters of a simple linear regression model. The slope, m, is calculated using the sums of x, y, x squared, and the product x times y. And the intercept, c, is easily found once we know the slope, using the means of x and y. These equations, known as the normal equations for simple linear regression, provide a direct way to find the line of best fit for any two-dimensional data set. Thank you for watching.